sunspots look like, and I'll point out the culprit of all the news items this past week with the geomagnetic storm and the auroras and all that. It was this spot group, which is now rotated over to the west limb. It'll probably be gone in a couple more days. You'll see in a moment. Okay. I'm just going to point out before I do that, I'll get a little better centered. So you see that some of these spots are closer to kind of they form in groups. So this is be like, well, actually this is two separate spots. And this is one group, here's another group, here's another group. And of course our big spot is another separate group, a small one. So a lot of spots these days, as we are now at a period that we call solar maximum. We're either at or very close to solar maximum. This year, next year will be probably the busiest with solar activity. So solar maximum is the peak of every cycle, 11-year sunspot cycle. We're started this cycle in 2019 at solar minimum. So at minimum, there's few or no spots for a long time. Eventually, you start to see a few spots, and then more and more as you get further along and reach a peak, as we are now. And then things reverse. You get down by 2029, somewhere around there, we'll be back down to solar minimum, and a new cycle will be starting from that point on. So today's spots, then I can demonstrate how those, how they compare to the Earth. So this would be Jupiter on our scale here. And then we have the Earth. Let's see if we can all see that. There's our Earth. Oops. Actually, we don't need the tape on there. Yeah. Okay, that would be Jupiter and the Earth. Yes, you see, quite a few of those spots are bigger than the Earth. So the big sunspot, actually now that is getting close to the western limb of the sun, looks a bit squeezed, because where our view of the sun, what's the sun being a sphere, so you see it kind of foreshortened as it gets closer to the edge. So, but earlier in the week it actually appeared much larger. So the largest sunspot that's ever been recorded occurred in 1947. Someone laid out this photograph of the largest sunspot ever recorded. Let's see. Yeah.
Wow. Did that cause interference with communications and things?
It did. But however, in 1947, we didn't have satellites around, so it was not so much big an issue as it is now.
Yeah.
So while they did have big solar flares and CMEs back then, there were no serious consequences such as any mass power outages or damage to the power grid. But there were some effects on communications and navigation at that time.
So that actually is a spot that was cooler. So
yeah, spots.
Back up.
Spots are basically cooler areas.
Yeah.
Wherever you see a sunspot, that's an area of a strong magnetic field that causes a cooling of that area. So compared to the rest of the solar disk, that cooling causes that area to appear darker. So that's why we call it a sunspot.
So then it heated back up and shrunk, right? So then what makes it heat up?
No, it's just that sunspot, the magnetic fields change.
It's changed, okay. So like change the temperature, distribute it differently.
And it just depends on how that area of the sun is behaving. If the magnetic fields are growing, and you can have more numerous spots forming there. If it's been around for a while, then the magnetic field is decaying. Then you start to see fewer spots in that area. And eventually, it'll be just appear like nothing on that part of the sun where there was a spot.
So does the sun not have poles then? Is there no...
Yeah, the sun has, there's a north and south pole to the sun.
And are they magnetically
Aligned?
active?
Well, there comes a time when there's a reversal happens with the magnetic field, but you never see really sunspots that are near the poles.
Okay.
Most of the time, sunspots are falling within a range either side of the equator. At the beginning of the cycle, spots are at high latitudes either side of the equator. Towards the end of the cycle, the new spots formed are very close to the equator, or the south of the equator. So anyway, this telescope has been used in what we still do as far as studies. Magnetic studies have been the primary kind of research work that's been done over the many years. Keeping track of the sunspots actually started, the record keeping of sunspots began around 1917. This is a drawing I did earlier, showing all the spots that you currently see. Okay, before I think I missed one thing about this big sunspot. So with the sun rotating, really big spots can last a long time, like more than one solar rotation, which is about 27 days. And so, get out of there, bug. So when this big sunspot was seen go across, it disappeared from view, and a little less than 2 weeks later it emerged again for the second time. And it went around again and did it third time, fourth time. So this holds the record at going 4 times around 3.5 months duration. Right now, it's possible that could come around a second time, but we'll see. We'll see what happens in a bit over 2 weeks from now. There probably is another spot that was around a couple of weeks back that was not as energetic as this one, but it did produce a number of solar flares that, number-wise, those number of flares had been the first time since, I think it was 2005, that we had that many solar flares for this new cycle. So anyway, okay, so the drawings then are one way that we keep track of the sunspots. So I said 1917 is when we started keeping them in this form, but a lot of other work was going on simultaneously with this telescope. But these drawings we've kept the tradition of doing them because they don't require a lot of high tech, and as long as we have a supply of paper and pencils to do it.
Sharpener over there,
Yeah, old-fashioned sharpener. So, and so they're useful as a data set because we have so many years now, well over 100 years of these records. So the researchers that like to go through data sets of any observatory possible have used our data and kind of for whatever purpose they want to study the spots or the information that we gather, because not only do we draw the spots, but you see over on the table, there's a tool that we use that's called Stony Earth Disk. That's an overlay that will be mounted on here with the image all lined up, and from that then we can get positional information, where on the solar disk these spots are located, and that information can be helpful because then you can find out where do surveys. Where do most of the spots fall on the disk and that kind of thing over the many cycles that these have been done. And then with the magnetic information, which leads me into telling you a little bit more about the telescope, how we utilize the light of the sun with our spectrograph. So you're looking at the top end of the spectrograph, and underneath this whiteboard and the table is where the light goes in through what's called the entrance slit. It's a narrow slit, and the light enters, and then down at the bottom of our 80-foot pit, we have our diffraction grating. Now I do have a laboratory grating, an old one that's good for demonstration purposes. But if I hold this in the light path here, and if you look over on the wall here, you can just see the spectrum there. You're going to get a longer one, do it this way, but you get the idea of what the grating does. It spreads the light out in all its colors to give the spectrum. Now, what we have below does a far better job of it in spreading that light out in its component colors. If we were to lay out that photographs of that spectrum out, it would be about 150 feet long. So here's one photograph of one area in the green part of the spectrum. And when you're measuring magnetic fields of the sunspots, we zero in on a pair of iron lines in the green part of the spectrum. Right here are the pair, this pair here. So I work with the iron line, and for every spot, the spot is moved right center over the slit, so that when I look through an eyepiece here at the spectrum, which is coming up to this level, and I'm seeing that iron line, I see what happens to it. The magnetic field of the spot causes a splitting of the line. It's called the Zeeman effect. So by using this technique of measuring how much splitting of the line, you can get derive the magnetic strengths in all these sunspots. And on the drawings, there's a lot of numbers. Those are magnetic measurements. Also, polarizers are used to see, get the magnetic orientation of that magnetic field, where it's positive or negative. And that's also designated on these drawings. A more modern way of doing magnetic measurements developed back starting in the 1950s, and by the early 1970s, when computers were becoming affordable, we actually still have that computer. It's a relic now, and through the doorway there's a 1970s era computer, tape drives and this sort of stuff. We were able to utilize a method for scanning the solar image to get a complete mapping of magnetic measurements, observation called magnetogram. So the magnetograph instrument is this white box here. It contains the detectors of electronics, and that coupled with a computer that ran for 40 years, we obtained data we have examples on the back wall of the magnetic maps. So the magnetograms, also another component to the observation was Doppler data. We could measure the sun's motions, the differential rotations as the sun rotates faster at the equator, slower at the poles. Superimposed over that rotation rate, we had other subtle motions that gave us more clues as to how the sun behaves internally, and motions that show up in the movement of the solar plasma, which were not that well understood, but through many years of our measurements, we gained information that helped in better understanding. So lastly, on the toolbox, we have the bust of George W. Hale. Over here we have photos of Einstein. This is in 1935. In the center